Timestamps require the ability to find the current date and time. The generation of logs, audit trails, and event trails requires the ability to annotate information with the current date and time. For example, a file name can include a timestamp to enable browsing for the most recent version of a file. Timestamps are automatically generated by the data grid and saved as system attributes whenever a file or metadata value is created or updated. These timestamps can be retrieved to find files that have been created after a specific date. In the iRODS data grid, time and date are specified in two different ways. In the Unix format, the number of seconds since January 1st, 1970 is saved. In the human format, the date time is specified as year, month, day, hour, minute, second. The iRODS data grid supports three routines for getting the current date and time. MSI get ICAT time *time, Unix gets the date and time from the ICAT server and returns the Unix format in the workflow variable *time. If the parameter Unix is replaced with human, then the date and time is returned in the human format. MSI gets system time *time, Unix gets the date and time from the iROD server and returns the Unix format in the workflow variable *time. If the Unix parameter is replaced with the word human, then the date and time is returned in the human format in the workflow variable *time. Time gets the date and time from the iROD server and returns the Unix format. The number of seconds from January 1st, 1970 to October 26, 2015 is 1,448,551,356. To calculate the difference in time between two dates, the Unix format is used as the values can be directly subtracted. Otherwise, the human format will need to be converted to the Unix format. Note that the time variable should be used as a double because of its size. The iRODS data grid stores date and time in a datetime variable. This is a structure that tracks the separate components for year, month, day, hour, minute, and second. To convert a datetime variable to a string, use either timestr with the workflow variable *time or timestrf with the workflow variable *time and a format specified by year, month, day, hour, minute, second. You can modify the format by shifting the order or deleting items from this formatted list. The timestrf allows you to specify the format for the string by selecting or rearranging the datetime format. Note that query results come back from iRODS as a string. To convert from a string to a datetime variable, use either datetime or datetimef, again where you're allowed to specify the format you want to have returned. The datetime stored as persistent state attributes are stored in the Unix format. Timestamps exist for collection, files, metadata, resources, and tickets. The persistent state attributes listed here can be queried. Call createTime, the creation time for a collection. Call modifiedTime, the collection modified time. Data create time, the file creation time. Data modify time, the file modification time. Data expiry, an expiration date time for a file. Metadata create time is the metadata creation date time. Metadata modify time, the metadata modification date time. Resource create time, the resource creation time. Resource modify time, the resource modification date time. Ticket create time, the ticket creation date time, and ticket expiry, the ticket expiration date time. When a Unix file is imported into the iRODS data grid, the date timestamps from the Unix file system are also captured and stored in data file meta ctime, Unix file create date time from the file system, and data file meta mtime, the Unix file modify time from the file system. If the clocks are synchronized, these attributes can be used to determine whether the copy in the data grid is newer or older than the copy on the file system. The rule shown here converts from the Unix format for date and time to a human readable format. The first test uses the MSI get system time microservice to get the time in Unix format. This is converted to human format but only retrieves the year, month, and day. The second test gets the time and date from the time function as a datetime variable. When the time is printed, it is automatically converted to the human format. The third test gets the MSI get systime microservice to retrieve the date and time in the human format. The fourth test retrieves a data modify time attribute from a file in Unix format. The fifth test retrieves the data create time attribute from a file in Unix format. All of the times are printed to standard out for comparison. Note that all date times retrieved from the metadata catalog are returned as strings. The createLogFile function policy is shown here. We've previously looked at this same policy function. A check is made to determine whether a collection already exists for storing the log file by using the isCall function. If the collection does not exist, it is automatically created by the isCall function. The function retrieves the current time in human format and appends the timestamp to a file name to create a new log file. The timestamped log file is then created. Take 7 minutes to complete exercise 52. Write a rule that gets the system time in Unix format, converts the time to human format, and prints the result. Please load your rule file into the lifetime library in the subcollection class INLS 624 by the end of today's class. EMC is a storage vendor that provides enterprise-level data storage. EMC is investigating systems for managing software-defined infrastructure. An example is a policy-based data management system that allows policies to be created for managing information and data. EMC is a member of the IRODS consortium and has the goal of integrating their storage products into data grid technology. Their initial efforts have focused on the development of a web browser interface called Metalinks, which simplifies management of a data collection. EMC plans to rely upon metadata management within the database to minimize storage requirements by managing migration to dark archives, index file systems to support fast search and discovery, automate file processing, define the preservation context, and manage secure data sharing. Since data collections are growing internationally at the rate of 2,000 petabytes per year, the ability to manage the data collections is becoming essential. An expected result is the merging of library science with information science concepts to manage both data and information. A major market for storage is genome data management. The requirements imposed on genomic data require policy enforcement that is not possible with only a file system. Types of policies that EMC needs to support on their stored data include IPR rights enforcement, including auditing as well as control, archiving, including creation of archival information packages, auditing of transactions, policy compliance and usage, disaster recovery based on replication and checksums, curation, including generation of provenance and descriptive metadata, collection formation, including naming and arrangement, federation, including interoperability with multiple types of external systems, and processing, including automated execution of workflows to create derived data products. As collections grow in size, the processing of data may need to be co-located with the storage systems. For tasks that have sufficiently low complexity, number of operations per byte, it is faster to do the processing within the storage controller than move the data to a remote compute server. Examples of low complexity tasks include pattern recognition. Data is streamed through an algorithm that tags the occurrence of each pattern in an external index. If the pattern recognition rate is as fast as the data streaming rate, doing the processing within the storage system makes sense. Types of pattern recognition include phenotype, structural, and subject tagging, and research annotations. Analyses that may require higher levels of processing or the identification of information across multiple files include population trends, summarizing information across multiple files, protein analysis and sequence generation, variation processing, identifying differences across multiple files, and reference genome creation, identifying commonalities across multiple files. Administration policies are equally important for storage vendors. EMC traditionally focuses on simplifying the administration of their storage systems. Tasks include monitoring of the server status, correction of all identified problems, and management of the total storage to track expansion requirements. Administration also includes management of information about users, including the creation of new accounts, creation of user groups, and enforcement of access controls. A system administration interface supports these activities. EMC designed the MetaLinks browser to support both collection administration and storage administration. The collection administration focused on mechanisms to support browsing across user attributes, collection contents, and types of metadata. The ability to search metadata for specific files that have the required attributes was included. For large collections, the ability to support bulk uploads and downloads is critical. A large collection is very difficult to assemble if every file is loaded one by one. The challenge is the management of the associated processing that must be done for each file. Processing steps include creation of checksums, replication, metadata extraction, and verification of compliance with metadata templates. A standard approach is to bulk load the files into a staging area and then apply the processing steps once the files have been moved. If the processing steps can be executed within the storage controller, the time needed to create large collections can be minimized.